In the last video, I talked about Biot-Savart law, which tells you to find out the magnetic field due to a current carrying wire. And in this video, I will use Biot-Savart law to find out the magnitude and direction of a magnetic field due to a straight wire. So here we have a straight wire here, and we are interested in finding out the magnetic field at point P due to this wire here. So the distance of the point P from this wire, the shortest distance between this wire and the point P is x. So that's the shortest distance. And in order to find out the magnetic field due to the entire wire, we are first going to choose an elementary length here, dy. That's the elementary length. And we'll find out what is the magnetic field due to this elementary length, due to this elementary current carrying wire at this point here. In other words, we'll find out the magnetic field due to this tiny segment at point P. So the length of the tiny segment is dy, and the direction, this direction, is in the direction of the current. Phi is the angle between this tiny segment and the distance here, or the r vector. So this phi is the angle between dy vector and r vector here. All right. So now let's write down, or let's use the Biot-Savart law. So what does the Biot-Savart law tell you? That the magnetic field at any point due to a tiny segment is given by this equation here. This equation here. And mu0 here is a constant that is called the permeability of free space. And dy here, dy is the tiny segment. R unit vector, this is the unit vector. Unit vector which tells you the direction of r, which is in this case. This has a magnitude of 1. Let us take a look into this triangle here, right angle triangle. This is x, and the distance from origin, in other words, let me mention here. So the length of the wire is 2a, is the length of the wire, and we have chosen this halfway in between as an origin, and this is my x-axis and this is my y-axis. Okay, so the point P is in the middle of this wire. It could lie anywhere, but just to make life simpler, we have chosen in between here. All right, it can be here, it can be here, and everything will be included in this video too. All right, so once we know y and x, then the distance will be x squared plus y squared. That's what I've written here. R is x squared plus y squared. If we know this angle phi, then this angle will be pi minus phi, or 180 minus phi. The sine pi is equal to sine pi minus phi, just from the trigonometry. And if you look into this triangle here, sine of this angle will be opposite divided by the hypotenuse, which is x over r. In this case, x over r. R is x squared plus y squared. And this is the magnetic field due to the tiny segment. So the magnetic field due to this entire wire, due to this wire, can be given by the integration here. So now let's take out, so all the constant terms out. Mu naught is constant, 4 pi is constant, even I is constant. In this case, we have assumed I to be constant. But in many cases, the I not necessarily to be a constant. It can vary as well. All right. So the magnitude of this magnetic field is now given by, so these are the vector quantity. So we have to take the magnitude of these things, dy vector cross r vector, and I, as I mentioned, is a constant, so I'm just taking I out. This is a cross product, dy cross r vector is a cross product. How do you define the cross product? If you have two vectors, a vector and b vector, then the cross product of these two is defined as ab sine theta, and there is a vector 2, and this is the magnitude ab sine theta. So in this case, the magnitude of dy and the magnitude of r is just the 1, and the angle between them, if you look at the dy vector and the r vector, the angle between them is the phi, so sine phi. So just written sine phi here. R square is x square plus y square. All right, okay. So now let's plug in all the values now. So mu 0 I 4 pi, this is as it is, and we have to now integrate here. We have to now integrate. You see, in this case the variable is y. This is the variable here. So let's first write down here dy as it is, x square plus y square. We have here sine phi. The sine phi is, we just calculated, x divided by x square plus y square square root. So this is it. So now look at in this equation, what are the constant? X is a constant here because x is the shortest distance between the wire and the point P, so that is a constant. So I have taken this constant here. The only variable we have is the y, and look at the limit of the y. Y is the direction along y axis here, so the limit is from negative a, so it can vary from negative a to positive a. All right, so that's the limit here. It can go from negative a to positive a. That's the limit. As x is constant, I'm taking it out. And now if we multiply these two together, the power of this one is 1 and power of this one is half. So if I add that together, it will be 3.5 here. All right, and the integration of this one is given here. If you have dy y square plus minus y square 3/2, and this is the integration. Okay, so here is my integration now. So instead of a, we have x here, so just plug in, instead of a we have x, and the rest is exactly the same. All right, and I just plug in all the values here, a and negative a, or simply this is symmetric about the x-axis. So this is symmetric about this axis, so this side and this side is symmetric, so I can simply do multiply by 2 and plug in the values of, instead of y I'm plugging a here. 2a, x is constant, x will be y squared, and instead of x I plugged in a, and the 2, because if I just plug in negative a, this term will be doubled. So solving further gives you mu naught I, 1x and 1x will cancel out, mu naught I 4 pi x, and 2a x squared plus y squared. And this is the magnetic field due to a wire whose length is 2a, of a length 2a at any point P. Okay, so and here the only thing that we have used is the Biot-Savart law, and the rest is the math. So now let's assume what happens if the wire is very, very long, infinitely long. Let's say, when I say infinitely long, that means let's say the wire is 1 meter, and the wire is 1 meter and the point is 1 millimeter. In comparison to this distance, this is very, very long. If you compare 1 millimeter and 1 meter, it's 1,000 times. So that we can consider as an infinitely long wire. Or if this A is the length here, right? A is this distance here, the length, half length. If A goes to infinity, or if the wire is extremely long, then let's see what happens to the equation. So mu naught I divided by 4 pi x as it is, 2a, and I'm dividing both sides by a squared here, or and you see like the a goes cancels out. So if I do that, then x squared over y squared as it is, a squared over a squared will be 1. And if a goes to infinity, then this term will be 0, this term. So this entire term will simply be 2. And if it is 2, then 2 4 pi will give it 2 now. So this is now further simplified to this equation here. And remember, I will say make a note of this one. This is the magnetic field due to a long wire. When I say long wire, that means it's a very long wire, infinitely long wire. Okay, so this is the magnetic field. So far and this is the magnitude. X is the distance between the wire and the point here. If it is infinitely long, it doesn't matter where the point is, if it is very, very long wire. So we found out the magnitude of the magnetic field due to a long wire by using the Biot-Savart law. Now let's find out the direction. Finding out the direction is pretty straightforward. What we have to do is use the right hand thumb rule or right hand curl rule. So what we have to do, hold the wire such that your thumb is in the direction of the current. Then all the fingers curl in a direction that gives you the direction of the magnetic field. In this particular direction, so this curl here gives you the direction of the magnetic field. That means if I have to find out the magnetic field at this point, it will be this way at the tangent. If I have to find out the magnetic field at this point, it will be tangent along this one. That means the magnetic field due to a current carrying wire or a straight wire is encircling the wire here, or it is circling, it's a loop around the wire here. And if I have to find out the magnetic field at this point, just imagine here, that means if the wire is onto the plane here or onto the iPad, then the magnetic field will be into the iPad here. So if this current carrying wire is in your iPad or in your paper, then and the current is passing this way, then the magnetic field will be into the paper just by using the right hand thumb rule. So this is it from this video. So in this video, we just talked about how to find out the magnetic field due to a long wire or due to any arbitrary wire of certain dimension, certain length. We also found out the direction by using the Biot-Savart law. So this is it from this video. If you have any questions or any comments, write down in the comment section below. And do not forget to like, share, and subscribe the channel. Thank you very much.